Hello everyone, today I am going to deliver a lecture of design on compression member, which is column member, and then second part I will cover the effective length factor of compression member. So let's start from a design of compression member. So here is some theory. Before I'm going to the explaining the example that I'm trying to some describing some theory. Let's start. There is some different name of column or different name of the compression member, which is we can say the stanchion, post, strut, pillar, cord, buttress, pier, pilaster, and baluster. These are the all our names are the compression member are all our names of the column. So we can see another the synonyms of the beam. We can see girder, joist, purlin, stringer, cross beam, uh, grist, and lintel. All these varieties names are synonyms of the of the beams. So we can see here the another picture. So this is the very short hook. It is fully plastic. When short is elastoplastic, then this type of hinge will be formed. When long column is when the column is long, then the buckling will be occur. So different phenomena is occurred. When the column is medium, then elastoplastic will be occurred. So you can see the hinge is formed. When the column is very short, then fully plastic will be occurred. So we can see here the some Euler elastic buckling. We know the formula pi equal to n square pi square ei by l square. So n is the number of mode. We can see the number one mode. So if we put this one, so pi ei by l square. So here is a two mode. So buckling is two. So if we put in n equal to 2, then found 2 square is 4 ei by l square. We can see here there are three mode, number 1 and number 2 and number 3. So it will be 9 ei by l square. And the same way we have been seeing the 4 mode 1 2 3 4. If we the column the compression member is to buckle this for in the phenomenon 4 mode, then it will be 16 ei by l square. So here is some effect of yield condition. We know the picture of yield condition, which is hinge is from the yield condition is hinge. You can see the two are hinges. The critical buckling will be n pi e square by pi square ei by l. So k, what is the value will be k? K is 1. Okay. So here another one is fixed, one end is fixed, another one is another end is hinge. So the critical buckling formula is remains it by square n pi square ei by l square, but the change will be k. K will be 0.75 l. So we can see k equal to root over l by root over 2 for our assumption purpose. Another condition we've been seeing the two end are fixed, so it will be the value will be k will be 0.50, or we can see l k equal to l by 2. On the other hand, we can see the fixed one end fixed and another is free, so the k value will be 2l, which is k equal to 2l. So this we can be memorize another thing. The strong axis k equal to 1 and weak axis k equal to 0.50. We have to must be memorize this. So let's see, here is the local buckling. The local buckling phenomena where the partial section of the column or beam buckling instead of the overall buckling. Okay, local buckling is a phenomena which is by which a portion of section of column or beam buckle instead of overall buckle. Okay, so it is a portion of the section of will be buckle. Okay, based on the width and thickness, the ratio is still section or depends on compact section. There is a compact section and non-compact section. What is the compact section? The compact section react is a cross-sectional material strength or capacity before local buckling. And non-compact section, it is a non-compact section only portion with a cross section reach with yielding strength before the buckling. So if we see the another yes, into compact and so we are seeing here the compact and non-compact section in I'm just using ChatGPT. The compact and non-compact section as a classifier used to determine the structural member ability to resist buckle under the stress, and practically being stress. These are the classification of width to thickness ratio section of compact. So compact section is defined, we have been seen here, the defined as a section where the element with a flange or web are proportional such that can fully develop plastic movement without local buckling. The behavior is ductile perform and the sustain large, and criteria width to thickness are ratio are below the specific limit close to core. Wide flange beam with adequate thickness and flange and webs. Non-complex section, a section where the element are the slender enough and local buckling occur before plastic capacity. It is rich and after the yielding movement. So behavior is a limited duckline and buckling reduce movement, and this may be form an adequate elastic and criteria. So we've been seen here is the some example compact and non-compact. Okay, so let's see if you have any compact and non-compact example. As a, consider the flange with wide flange beam. W section is the following properties is given here. So calculating the width to thickness we've been seen 10, and if the check as per ASC 3616 figure compression in bending. So we've been seen compact section 0.308 EI by FY, and we have been found 220. On the other hand, non-compact section we have been we are seeing the P by T is 10 and found 220, which is compact. So another section we have been seeing here 10 is less than 550, so section is still compact. So if we consider this formula is given to the if 10 is greater than this formula, then we can see the non-compact section. So I hope that you can understand the compact and non-compact. It is important. Slender, it is a section which the cross section does not yield and the strength of the member is governed by the local buckling. And unstiffened element unstiffened it will be unstiffened element. The flange is supported one end and the free in another. Okay, this will be unstiffened, and stiffened element will be supported by both ends. So this is the unstiffened element and this is the stiffened element. Okay, so let's see the example here. The compression member, we can see the example. Determine the allowable compressive load carrying capacity of the column shown figure given below. It is consist of the W 10 15 section and having 1992, and there are the hinge supported top and bottom and allowed to rotate in one lead direction. Also column has weak direction in supported brace at the mid height, and so that lateral deflection of prevent the x direction. Use the ASTF process. You can see here is the given the figure. You can see the load is given applied in axially. So x-axis and y-axis is given, x-axis and y-axis given. When when section is W10 50, then we have been found a r x r y from a seminal like this, but we will select W10 45. So if we go to the W10 45, where is the W10 45? W1045, this is the W1045. So we will found the area 13.3, area 13.3, and rx ry will be come from here, or second portion, this. So rx 4.32, 4.32, and ry 2.01. This is ry, ry 2.01. So in this way we can take in this from AIS manual. I am not showing again and again, so as far I am giving first time. So x-axis is the strong axis, because a value of rx is more, and y-axis is weak axis because the value of r is less. So rx equal to root over I by a, as we can know that. So column length we know the 13, and it will be in 2, as far is given in here, and it will be multiplied into 12, and 312, and kx equal to 1 and ky equal to 5. As the constant value we have to must be memorized. The strong axis k value is 1, and weak axis k value is 0.5. So it is the memorizing value. And now we'll calculate kx into L, which is 7.72.22, and putting this value and found 133. So 72.22 is less than 113.43. So we will use this formula. Now we will use this formula and found f equal to 54.82. Now which is less than 50, which is greater than 50. So now we will use this formula and found 34.13. So nominal strength x-axis we are using here, and found 454 kip. For y-axis we know x-axis is 1 for strong, and y-axis for 0.5, and weak axis we will use ky equal to 0.5 as weak axis, and found this value and 77.6, and using this formula and found 113, which is less than this value. So we will use this formula and found f equal to 47 into 47. If we it will less than, then we'll change this formula, but the condition is satisfied. And FCR we will use this formula and found 32.17, and nominal strength x-axis we have been on 427.9. So we have been seen the x-axis is found 454 kip, and y-axis is 427 kip. So we will taking the small value, which is 427.9 kip, as the member will be collapse after the reaching the minimum value. So now we'll using ASD formula, and found 257. If we use the LRFD method, and found 3857. This is our answer. So you can see another example. The steel is lightest W section of A992 to steel to serve as a pin, and end and main member column 16 feet, and long to carry an axial compression load, which is 115 kip, and dead load is given 115, and live load is 125 live load, and brass structure and figure is given below. So this is the brass structure. So you can see the hinge support is given here, and the height length is 16. So P dead load plus live load is 220, and length is given. So if both these are hinge, so K will be 1. On the other hand, we can take a note this: if the hinge is then 1, and fixed hinge in 0.70 fixed, then we will use 0.50. If fixed free, then we will use 2. But we are seeing the hinges, that's why we are using 1. So first of all, we are assuming KL by R equal to 9, or 19, which is we are taking this assume 19 value which is below 100 or close to 100. Okay, so we can use 80 to 100, between 80 to 100 value, and founding R value is 2.19, 2.13. Now we are seeing here KL equal to 19, and this formula if we use then found 113. So the okay, and Fe we are using formula for Fe and found 33.33. Now we are giving the another trial, which is this KL by R we have been found 90, and 4.7 root over E divided by Fi, which is we have been found 113.43. So now if we can see that this formula is satisfied, that's why we will use this formula. If the condition is does not satisfy, then we will not this formula, we will change this formula. Okay, so we have been found 27.65, and allowable length we have been found 40, allowable strength, and normal strength is 40, and found L equal to 14.5 for using back calculation. Now we have to choose another section whose value is R greater than 2.113, as we have been found R value is here 2.13, and A is found 14.5. So we have to choose a section whose value A is greater than 14.5 and R value is greater than 2.13. So we have been writing is here in so now we are changing 1250 from AIC manual. If we go to the AIC manual 1250, then we can see the A value is 15.6, which is the greater than 14.5, which is 15.6, and RY 2.13 is given here, but RY, where is RY? RY is the next slide. RY is 2.448. So we are taking the 2.48. This is from AIC manual. We are taking from the greater than this value. I am not showing again and again. So now we are trying again, as I am assuming KL divided by ratio as remains same R, and found 2.41. And then we are using Fe formula, this formula, and found 14.44. Now we are using this condition, and if the condition is satisfied, then we will use this formula and found 13.31. And in this way Pn equal to calculated, and found Ag equal to 12.2. So now we have to select another whose section is 2. Greater than 2.4, and Ag equal to 12.8. So from AIC again we have been found another member which is 1049, and again we have been trying again, and assume the KL R value is 70. We are reducing this value and found R equal to this value, and F equal to 54. Now we are putting this value, and if the condition is satisfied, then we will use this formula, otherwise we will use another formula, and found 34.6. And the allowable strength we have been found in 40, and nominal after calculating nominal strength, and found Ag equal to 11.45. So we have to select another section which R value and A value is greater than N, and select the 12.65. So final result we have been seeing the trial 1, 2, and 3. We have been taking the 3 trial. When assuming the KL value is 90, then we have been selecting the section 12 into 15. When KL by R value is 18, we have been selecting another value which is 10 by 49, and another value we have been seeing the KL by R value, the ratio is KL by R is taking the 17, and found 12.65. So as we have been seeing the more economic, we have been seeing the the value is 14, which is more economic. That's why we will use this section, which has been found in trial 2. In the final chosen section is W, 10 divided by 14 as more economic. How will get the more economic? Because the section was less. If the section is big, then we have to provide the more steel. As we know, the more steel if we use, then we have to provide the more money. Okay, so this now we'll check again is the local buckling. If we know we have been selecting this property, then we will find BF, TF and TF from AISC manual. I have already shown here how we'll get the value. So all are given here. And if we were checking this formula and found 3.8.99 is less than 13.3, so it's okay. Now we'll check the web using this formula and found 22.06 is less than 35.9, so this is okay. So now see another example of column design. Select the lightest W section from the table below AM9.50 and serve as a column as a 25 feet length and carrying the axial compression 58 kip dead load and 158 kip live load in brace frame structure, and column is assumed to the fixed in top and bottom. So this is the fixed. As we know, dead load plus live load 58 plus 150 is 216, and allowable strength we have been known, found in this formula 240, and length is found is 300 and bond is in fixed. That's why you will use 0.50. If we found the hinges, then we will use 1, and fixed. If we fixed in the hinge, then we will use the 0.70. If we fixed fixed, then use 4.40. We have been taking this, and fixed free, then we will use the 2. This is the memorizing chart we have been found here. Now we'll assuming cal divided by R ratio is first we have been taking for 90, and second trial we will taking 80, and third trial we will taking the 70. So and then found F equal to 35.5 and FER found 27.65. So now we'll calculating FCR, FPN by AG, and found as value which is 8.60. Now we'll, if the AG is value is 8.68 and A value 1.65, we have been found here 1.67. And now we'll selecting a section which is found from AIC manual, which is A value is greater than 8.64, which is 12.6, and RY value is 1.89, which is 1.67 is found. And this is the first trial. And the second trial we are taking 80, and in the same way we are calculating and found the R value, and FE equal to found here, and FCR found, and putting on value, and AR area is found. So 2 parameter R and area if you found, then we are taking the another section from AIC manual, which is value A and R value is greater than this value, and selecting this value. And the same way we are taking the trial 3 and found R value is 2.14, and putting in this way FCR and AG is found 6.87. So now we go to the AIC menu, which value is R is greater than 2.14 and AG equal to 6.87, and found select this member. So finally we are we've been seeing trial 1, trial 2, and trial 3. Sorry, I'm writing wrongly. Here is the trial 1, and here is the trial 2, and the last one is trial 3. We have been seeing when the KL value is taken 90, then we have been found this for this value, and the area is 12.6, and when we taking the ratio L divided by R is 18 and found for 14.1, and the 17 and found 17.9. So we have been seeing the less. We are selecting the less area for the economical purpose. So our final selection will be this section. So final choice we've been selected 14 into 43 as the more economic purposes. So we've been, if we select this section, now we're taking all the parameters from AIC manual. For checking flange we are using this formula and found flange is okay. We are using checking web and using this formula, and we've been seeing that this is not okay. So we have to recheck, we have to select the another section. So okay, the compression design of compression member or column member is completed. Now we'll see the effective length of K factor of compression member. Okay, so effective length of K is compression member. It depends on the yield restraint and sway condition. So we've been seeing the effective condition K of the compression member is given in condition and unrestrained, and one in condition and one in condition and restrained, and one is unrestrained, and one rotational fully restrained and partially restrained of each column we have been seeing here. So K equal to 1K and KL equal to 0.7L and 0.5L and less than greater than A. So relative stiffness column, which is G equal to EI divided by L is column, and EIL divided by beam or girder. So you can see the stiffness of column and stiffness of beam. The ratio of stiffness of column and stiffness of beam is called the relative column. So we can see the stiffness modification factor for beam. Here is the some condition for end of beam, the hinge supported unsway side sway of column which is unbraced. If you unbraced, then we will use 0.50. No side sway of column or braced column, then we will use 1.5. For end of beam, the fixed support, unbraced we will use 0.67 and braced we will use 20.2. For the end support we have been seen here the rigid, then condition will be unbraced will be 1 and braced equal to 1. So another important things is here for end of the beam, the hinge supported, then G will be 10. This is the fixed value we have to memorize. And end support of column which is fixed support, that will be use 1. These two things are must important. So if the hinge support, then you will use 10G, and if it's the fixed support, then you will use 1G. Let's see the example, then you will be clearly understand. So here is the another example. You can see they calculate the effective length factor K in the frame section is given below. Use the alignment chart of nomograph using AIC table of data. So you can see here the frame structure, but it is the this is another support. So in this for this support we can say the this 3 column will not be going to the sway as the breast is connection. So AB, so you can see AB. So non-sway must be writing here non-sway, because we've been seeing the another support is given here. That's why AB is non-sway. Okay, so GA value will be 1. Why 1? GA value will be 10. Why? The hinge support, as we have been seeing the hinge support, that's why you will use 10. This is the fixed value. And if we find the fixed support, then it will be value will be 1. So GB will be we are calculating GB, which is EI is going to the clause I is given. Here is I, the one section, all the section is given. So now we are calculating GB, which is the where is the GB? This is the G. Column AB. This is the AB. So AB column we have been found 0.31, 8 into 0.31 this section, and I equal to 113. I equal to 113. And we have been seeing the this section is beam is given, which is 18 into 50. This is the beam. As we know the ratio between column and beam, so beam is given 300 into L is 30, so this is the length of 30, and this length is 15. In the upper portion is length 15, column 15, and found 2.275. So GA1 is 10 and GB2 0.275. Now we'll go to the nomograph. So I'm putting here the nomograph. This is taken from Salman books. So if you know that this is the non-sway, so we are selecting the non-sway. This is the breast and unbreast. So breast frame is non-sway. One is found point 10. So if we go to the 10, GA value which is 10, this is the 10, and another value we have been found 0.27. If we go to the 0.27 is 2 and 27, okay, it will be 27. And if we intersect this two lines, then it will be found between 0.70 to 0.80, and we have been found 0.75. So in this way we have been chosen 0.75 from nomograph. I will not seeing the again and again. This is the breast fresh, that's why we have been found this. If we use the unbreast fresh, then we will found another value of K. But one thing is the breast say the K value is 0.5 to 0.5 to 1. So breast value of breast must be less than 1. On the other hand, unbreast frame the K value will be must be greater than 1 to 20. So must be greater than 1. So this is the assumption value. For non-sway value, we can see in the by another section. We have been seen the CD value. This is C and this is the D, and we are taking 10. Why? Because the hinge supported. This column is hinge supported. That's why taking the 10. And the at point G, so this point we can calculate this point D. The column we have been seeing the two columns. Columns is CD and E and DE. So we are taking CD and DE at the value is the remain same 331. So I value is remain same. I 110 and 110, and the height is different. We have been seeing the CD is height is 15 and D is height is 12. So 15, 16 and 12 is given. On the other hand, we have been seeing the two beam 1 and beam 2 is given here. So 800 I moment of inertia is given high 800, and length is 30 and 20. So that's why you have been used 30 and 20 and found 2.247. And if we get that one third 10 and 0.275, then we will use the nomograph this graph at 10 and 0.27, and in this way in the found the K value 0.74. So we can see another in this way we will calculate the soy DE value, which is DE. This is the soy. Why this is the soy? Because we have been seeing that there is no bracing, or there is no bracing is here. On the other hand, the wall the column is non-soy because of this support. In the top portion there is no bracing or no support, and that's why this will be soy. And in this way we are calculating, we already calculated GA value 0.275, and now we are calculating just at point E. At point E, this means this point of E. So we are calculating in this point E and found 0.63. If we from this ratio, we will calculate the stiffness of K. This is soy, so the value will be K is greater than 1, as we have been seen here. We will using this graph, not this, because this is the breast or soy non-soy graph, or this is the unbreast or soy graph. So okay, in this way we will use then another non-soy graph which is given is here, and in similarly we have been found, and in this in this way calculating all of this here. So another another calculation means in determine the effective length of the column of the frame is showing below, and we've been seen here the bracing is here. So now we have to calculate which is the soy and non-soy. So column AB, so this is the column AB which is non-soy because the brace is induced. So we've been seeing the pin support, that's why you will use in 10, and GB at point P we are calculating here the column 1 column and 2 column, and beam divided by column column divided by beam. So we have been found the column divided by beam is 1 beam, that's why we will use 1 and found 2.3, and using 2 value use the nomograph and found K value. As we are doing the CD is also non-soy. Soy, there is no bracing. If we use the bracing, that then it will found non-soy, but there is no bracing, that's why it is the soy below. So and as a pin in the fixed support, that's why we will using 1. If pin then 10 and if fixed then it will be 1. This is the memorizing one. And D point we will just calculating D point. There is a 2 column columns and divided by beam, they are divided by beam, and found this value, and respected to from this value we will calculating stiffness. And BE and DF is also soy. BE and DF also same below. In DF there is no bracing and there is no supported, that's why we will use we are considering this is the soy member. And found use B point, we have been seen here the 1 column and B point there is 2 column. If you consider B point, this is the 2 column and 1 beam here. And if you consider E point, there is the 1 column and 1 beam, and found this below. And then last one we have been seen here the calculate the effective length 10 kg. We have been seeing CD is soy. How will get the soy? This is the CD because their portion no bracing. This will be also soy, and the bottom portion is non-soy because we have been used the this what I will say this support. And CD is non-soy soy value we have been seen here as point D we are calculating, found column 1 column and 1 beam, and here and point C here is a 2 column and 1 beam, and found 2. And in this way from this value we are calculating stiffness. And kg we have been seeing here. Kg, where is kg? Kg, this portion also soy we have been seen here at point K, where at point K if we calculating here 1 column and 1 beam, so 1 column 1 beam. 4 point J there is a 2 column and 1 beam, 2 column and 2 beam, and using this found this value and using this K. And another value is Ij is non-soy. So this is the important, this is the Ij, this is non-soy because of the using this support. As this support, the structure will be not buckle or not soy, not buckle. On the other end, the top portion will be buckle, and the bottom portion will be not buckle as using this support. So in this way, at point I we have been seeing that point I the fixed support, that's why you will using 10. You will using 1. If the hinge support will be ends and fixed support will be 10. And support J, this is the J, there's the 2 column and 2 beam. So we have been seeing 2 column and 2 beam, which is found 0.85. Okay. So when we get the GI1 and GJ is 0.80 0.85, then we will use 0.92 from nomograph. So this is how we'll get the 1.5. It depends on non-soy plus support column beam. On the other hand, we have been use 0.50. It is also depends on non-show and support. So that's all from me. If you have any, that's all the effective length of factor k is completed. If you have any question, then let me know. I'll try to discuss again. Thank you, everyone. Thank you for your patience and give me times and give me your valuable times. Thank you.